This is my thermochemistry review in preparation for the AP Chem Test 2019. And here's what triggers it. Last year, in 2018, they gave a thermochemistry problem, and there were other things in it, stoichiometry in it, and oxidation numbers and so forth. But they wanted to know, down here at the bottom, for this reaction between thiosulfate, hypochlorite, and hydroxide, they want to know the value of the enthalpy change of the reaction, delta H0 of reaction, in kilojoules per mole of reaction, including the appropriate sign. We need to look carefully at this because this is a model for all thermochemistry problems, and there's likely to be one on the next examination. So let's look at 5 questions you need to be able to answer whenever you see a thermochemistry problem. And you need to answer these questions in about 10 or 15 seconds as you do the problem. First, from the graph that they give you here of time versus temperature, determine whether the reaction is endothermic or exothermic. So think about that for a moment. As you see here, the temperature of the surroundings is increasing with time. That means the heat involved is coming out of the chemical system into the surroundings. That means it's an exothermic reaction. Second question, what is the temperature change of the surroundings, including the sign? You'll need that to determine the enthalpy change. Well, the temperature change is positive. Delta T is greater than 0. And when you do the calculations, 32.5 final temperature minus 20 initial, 12.5 degrees Celsius. Now please note, whenever you write a temperature change, show the sign, whether it's positive or negative. This may not be good math, but we shouldn't take any chances with thermochemistry. We must have a sign with every number. Third, the position of the enthalpy change, reactant or product. Where would it be if we showed it as a reactant, or product? Since the system's losing heat to the surroundings, the E of reactants is greater than the energy of the products. That means delta H is coming out, it's acting as a product. We would show it on the right side of the equation if that was the way we actually showed such things. What is the sign of the enthalpy change if we show it in the customary fashion as a delta H? Well, again, system is losing heat to the surroundings, so E of reactants is greater than E of products. Delta H, therefore, must be less than 0, and the sign is going to be negative. Another way of looking at it is, how would we show the enthalpy change, the delta H, in customary format? Same thing, system's losing heat, E of reactants greater than E of products. So delta H is the H of products minus the H of reactants. That means delta H is less than 0, and delta H would be a negative number when we show it out on the right as delta H equals something. Those are the 5 questions you should answer for every enthalpy question when you read it, and you should answer it in 10 to 15 seconds. Now let's look at the magnitude of heat energy given off. They give you the mass, 15.21 grams, of the surroundings. They want you to calculate the magnitude of the heat energy in joules released during the reaction. They give you a specific heat of the reaction mixture, 3.94 joules per gram degree, that is different from the 4.184 you're used to. Use the number they give you. Now, we're measuring the heat released, that's Q. It's going to be a positive number because delta T is a positive number. Q is the mass times the C, the specific heat of the reaction mixture, times delta T. And so you have 15.21 grams, 3.94 as the C, and 12.5 degrees is the temperature change positive. Therefore, with 3 significant digits, Q is plus 749 joules for this reaction mixture. Now, In a previous question, they wanted to know what the limiting reactant is, and they used the solution shown in the table below. Notice, each one of these has the same concentration and each has the same volume. That's good, because you only have to calculate the millimoles once. Now, they want to know what the limiting reactant is, and they want you to justify your answer. They don't ask for a number here, but you really need it. So let's multiply the molarity, that's millimoles per milliliter, times the milliliters to get the millimoles in each of these solutions. Well, 5 times 0.5 is 2.50, 3 sig digs, and now we can move forward. Now we need to know what the limiting reactant is, and so we should use a RICA table, and it takes about 5 seconds to set that up since you've already written the chemical reaction. We know we start with 2.50 millimoles of each of the reactants. Now we can look at the chemical equation and see that the sodium hypochlorite is disappearing 4 times faster than the sodium thiosulfate and 2 times faster than the sodium hydroxide. You get that from the coefficients of the equation 1, 4, and 2. So when we use up all the sodium hypochlorite, however much there is there, we still have, since we had the same number of millimoles, we still have 1.25 millimoles of sodium hydroxide and 1.87 millimoles of the thiosulfate left over. That means the limiting reactant must be the sodium hypochlorite. I've added the zeros in the RICA table for the 3 products. And now, once we've gotten rid of all of the sodium hypochlorite, we are left with thiosulfate and sodium hydroxide, because we've only lost 0.63 of the thiosulfate and 1.25 millimoles of the sodium hydroxide. Here are your excess numbers. We can now look to the balanced equation to show that since this is a 2 and that's a 2, we now add 1.25 of product, sodium sulfate, 2.5, there's your 4 and your 4, 2.5 millimoles of the sodium chloride, and there's a 1 and a 1, 0.63 millimoles of water product, giving you your final numbers here, showing therefore the limiting reactant. The next question is, using the balanced equation, calculate the value of the enthalpy change of the reaction, delta H0 of reaction, in kilojoules per mole of reaction, including the appropriate algebraic sign. This begins to make things a little bit complex, because now we want to know what constitutes a mole of reaction. We want the delta H. We have Q for that small amount of reactant. Well, let's look at a definition from a 1972 textbook. 1 mole of reaction has occurred when the appropriate numbers of moles of substances as specified by the stoichiometric coefficients on the left-hand side of the equation are converted to the substances on the right-hand side of the equation. When the change in the thermodynamic property is given for a particular chemical reaction or process, it always refers to a mole of reaction, not a mole of reactant. Looking at the equation, we see that if we want a mole of reaction, we're going to want to react 1 mole of thiosulfate with 4 moles of the hypochlorite and 2 moles of the hydroxide. Therefore, we want to look and see where is the 1 coefficient here, and that'll give us the answer to what is a mole of reaction. So we want the delta H in kilojoules per mole of reaction. Now, thinking about that, we need to ramp up to 4 moles of hypochlorite. The Q released in 1 mole of reaction is the Q produced by the complete reaction of this 4 moles of sodium hypochlorite with adequate amounts of the other two, so that nothing is in excess. 1 mole, 4 moles, 2 moles would produce 2 moles, 4 moles, 1 mole of products here. Now we have the number for 2.5 millimoles of sodium hypochlorite. That's a Q of 749 joules. This needs to be adjusted to the enthalpy from 4 moles of sodium hypochlorite. Well, we can do that. First, we adjust to the enthalpy from 4 millimoles of sodium hypochlorite. We multiply by the fraction 4 divided by 2.5, because we started with 2.5. And when we do that, we see that for 4 millimoles of sodium hypochlorite, we get 1198 joules. We want, however, a mole of reaction, not a millimole of reaction. So we take that number and we multiply by 1,000. We get then the enthalpy from 4 moles of sodium hypochlorite, because that's 1,000 times the 4 millimoles. The Q released in 1 mole of reaction is the Q produced by the complete reaction of 4 moles of sodium hypochlorite. And when we do that, we go from 1,198 joules per 1 millimole to 1,000 top, 1,000 bottom, 1,198 kilojoules per mole. That's what we're looking for. 1.2, therefore, times 10 to the third kilojoules per mole. The complete reaction, then, of 4.0 moles of sodium hypochlorite gives us an enthalpy change, since delta H is equal to minus Q, an enthalpy change of minus 1.20 times 10 to the third kilojoules per mole. And that is a mole of reaction, as we can see here. Now there's one more question they ask. If the student repeats the experiment and doubles the volume of each of the reactants, so doubles the millimoles of everything, the magnitude of the enthalpy change, delta H of reaction, in kilojoules per mole of reaction, calculated from the results of this experiment, is the same as the result calculated that we just got through calculating. They want you to explain the result. I'm going to leave you with that, because at this point, since you've gone through and you know what the enthalpy per mole of reaction is, it should be fairly easy for you to figure this out.